Okay, we'll get started. In this section, we're going to be looking at 3G, which is going to be Newton's first law. So before we actually get into the law, we get to get a little bit of vocabulary out of the way. And the first term is going to be inertia. Inertia, I-N-E-R-T-I-A. Inertia. And inertia is the property of an object to resist changes in motion. And changes in motion are really acceleration, or because they're technically changes in speed and or direction. So again, inertia, how much does the object resist changes in motion? If it's standing still, how much do you have to push on it to get it moving? If it's moving, how much do you have to push on it to get it to stand still? If it's going one direction, how much do you have to push on it to get it to change directions? So again, that's all dependent on inertia, how much force is required. Mass is going to be a measure of inertia. So if something has more mass, it's going to have more inertia, meaning it's harder to change its motion. So if you have a large object and then a small object, assuming they're made out of the same thing, it's going to be much harder to, get the large object to start moving, to stop it once it's moving, to get it to change its direction, than it is going to be to get the small one to, start moving, get it to stop moving, get it to change direction. Because the larger one has more inertia. So again, if you have more mass, more inertia, it's just basically harder to get it to do anything. So that's the vocabulary, inertia, and how it's related to mass. Newton's first law, we'll get into the law now, Newton's first law. So we've talked about the other two, the second and the third. First law describes an object's tendency to change its motion. And this right here is the wording about how it's usually phrased. So it says an object at rest tends to stay at rest, and an object in motion tends to stay in motion, unless it's acted on by a net force. So what this says, it's basically saying, I like to think of it as objects are lazy, meaning if it's sitting still, it's going to keep sitting still unless you apply a force to get it to start moving. If an object is moving, it's going to keep moving unless you apply a force on it to get it to stop. So it's basically saying whatever an object is doing, it wants to keep doing that. The only way to get it to change is really to apply a net force. So that's basically what it's saying. Now there's a couple kind of things that fall out of this. There's a couple consequences of this first law. The first is if an object has no forces on it, by Newton's second law, it's also going to have no acceleration. Acceleration. So again, if there's no forces on an object, it's just kind of there, no force, there's going to be no acceleration, meaning whatever it was doing, it's going to keep doing that. Could be standing still, could be moving, but it's going to keep doing that. There's no acceleration, there's no change in velocity. And if an object is not accelerating, so if acceleration is 0 meters per second squared, 0 acceleration, there must be a constant velocity. So again, if there's no acceleration, you're moving at a constant velocity, and that constant velocity could be like 2 meters a second, or negative 100 meters a second, or technically 0 meters a second. But whatever it is, whatever the velocity is, it's going to stay at that same velocity if there's no acceleration. So acceleration is what causes the velocity to change in the first place. And the last thing with this is the first law. The reason it is like a thing at all in physics, the reason it took a while to actually come up with, is that it kind of is counter to what we see on Earth. And what do I mean by that? Well, if you take a ball and you roll it along the ground, it's going to come to a stop eventually. So that seems, when you first think about it, that seems to violate the first law. You're like, okay, well, something was moving and then it stopped. How did that happen? Isn't it, if it's moving, doesn't the first law say it keeps moving? Well, the reason it comes to a stop is because there's a force of friction on it from the ground. There's also some air resistance, but it's mostly the force of friction that's doing that. So again, the reason this law isn't like super intuitive all the time is that, again, objects want to keep doing what they're doing unless there's a net force. And when you're on Earth, there's going to be friction everywhere. There's going to be air resistance. So basically, any object on the Earth or almost all objects on the Earth are going to have a net force on them. So whatever it was doing, right, there's going to be potentially, two very common forces acting on it. So that's something to keep in mind. Just because you see something slow down, doesn't mean the first law is wrong. That means that there's a net force on it, and that's allowed for by the first law. So just keep that in mind if the laws kind of seems a little bit strange. So that's all of the stuff really in the first law. So a little bit on inertia, the phrasing of the first law, a couple of the consequences that fall out of it, and just, a reminder that it's not, sometimes this law doesn't appear to be true on Earth, but it is. There are forces acting on objects that change their motion. So that's the notes. The last thing we're going to see here is a problem with this. So this is a problem. Before I go through it, make sure you try it out. At the very least, make sure you write out some of the knowns, unknowns, maybe a free body diagram. Okay, I'll go through it. So what do we have? We have a soccer ball, 0.5 kilograms, is moving at 2 meters a second across frictionless ice. How much force is required to keep it moving at 2 meters a second? So, ball, 2 meters a second across frictionless ice. So if we want to keep it moving at 2 meters a second, how much force do we need, basically? So we know the mass, we know the initial velocity, and we know technically the final velocity that we'd like. So how much force is required to do that? Well, if we think about it, let's maybe draw out the free body diagram. There's only really two forces, right? There's the normal force up from the ice, and there's the force of gravity down. The Earth is pulling on the ball into the ice. And there's really no horizontal forces. It didn't say it was being pushed. And it didn't really say anything about, and in fact it says it's frictionless. So that's something to keep in mind. So it's saying, okay, well it's moving 2 meters a second. There's no friction. There's no really other forces in the horizontal direction. So if it's at 2 meters a second, we want to keep it at 2 meters a second. Technically, we don't have to do anything, right? Because if you have an object, right, that's moving at 2 meters a second, the first law says it's going to stay at 2 meters a second unless there's something that's causing it to slow down. So again, if there's no friction, and we're not going to take into account air resistance unless it explicitly says. So if it's at 2 meters a second, no friction, it's going to keep at 2 meters a second pretty much forever unless it runs into something. So what do we get to do to keep it going at 2 meters a second? Nothing. We don't have to do anything. The first law says it's going to keep doing what it was doing before because there's nothing stopping it. So how much force is required? There is no force required. Technically, there's 0 newtons. So again, this was really a conceptual question. There's really no calculation here. It's just realizing that if you have something that moves at 2 meters a second, you want to keep it there. Nothing, it's no real friction or anything to stop it. You don't need any force to keep it doing the same thing. So that's about it. Make sure you have all the notes down. Make sure you have this problem down. And that's it for now.